Swayam Prabha. Digital India. Educated India.
Welcome to this lecture in soil technology. This is the last one in soil water regime. So we are going to discuss today about the flow processes for water in soil, typically saturated and unsaturated flow. We'll talk about the soil hydraulic properties. We are going to also briefly discuss about different hydrologic processes as they are related to soil water regime. So this is a very interesting topic because here we will quantitatively describe how or what happens to water when it moves through the soil. Little bit of background, if you remember, we have so far discussed about soil as a porous medium. We have discussed how to describe soil wetness in terms of gravimetric water content, that is mass of water divided by the mass of the soil, or we also can describe soil wetness in a volumetric basis, means we can talk about volumetric water contents as the ratio between the volume of water present in soil over the total volume of soil. And then also we have discussed how this water which stays in the soil is a result of the interaction between the soil particles and the water, and the resolution of different forces. So we have discussed about the water retention characteristics, and so this means that we have talked about the energy status of water in soil. So in that we have talked about different kinds of potentials. We have discussed that the potential energy is a major determinant of how water is held in soil. In other words, how water can flow through the soils. So when we talked about soil water potentials, we talked about how these basic principles of fluids, namely this surface tension, the way the contact angles are formed, these concepts of Laplace's equation relating the capillary pressure and the radius of curvature for the pore spaces, these meniscus that you have. And then of course we have discussed about how the rise of water into the capillary tube can be linked to this energy content or the surface tension and the capillary pressure, and so thereby we have discussed about the metric potential. So the potential which arises because of the surface tension, because of this capillarity, which is a result of course, this cohesive and adhesive forces that are present with as a result of the interaction between water and soil particles, soil as a porous medium in particular. So with these sort of background that we have built, describing how water relationships at sort of a static equilibrium, right? We talked about water retention characteristics. Every point in a water retention curve, we discussed that each point, whether it is a field capacity, whether it's a permanent wilting point, or any of those static soil wetness, are linked to one of their corresponding equilibrium state or static energy contents. So that's the concept of water retention characteristics, the relationship between how much water is held with how much energy is involved in holding that water in soil. So these issues that we have discussed pretty much looks at the static behavior of water in soil. We need to really though look at the dynamic behavior, because water which is present in soil is always subject to the losses of different kinds, whether it is an evaporation loss, whether it's a percolation loss, or even the way water is taken up by plants. Constantly the soil wetness changes with time. Constantly it changes from location to location, and therefore the flow of water through soil is one of the very important processes that we need to have a quantitative control, meaning we should be able to in a position to either estimate how much water is flowing, at what rate water is flowing, or we should be in a position to really directly measure how much water is lost from the soil, and so that we can really know the other part of it, how much water is retained. So this, water relations and water flow, they are kind of intricately related. So let us look at these water flow processes in soil. Um, if you look at the flow processes, primarily the flow processes can take place in two different ways. One is when soil is fully saturated, of course, or when the soil is unsaturated, means part of the pore space is occupied by water, part of the pore space is occupied by the air. So these are the two cases of saturated and unsaturated flow. The trivial case, of course, is there is no flow. Water is not moving, even whether it is a saturated condition or an unsaturated condition. Water does not move. So that is your static equilibrium, right? So this case A here is the static equilibrium case. The cases of B and C are the dynamic water flow regimes. So under the saturated flow, again, the rate of flow can be constant with time, which we call it a steady flow, or the flow rate can change with time, which is an unsteady state. Sometimes we also call it a transient state. So it is time dependent. So basically the flow rate changes with time. As the flow rate would change with the time, you might really come across situations where water content in the soil would change in time, because there is a one-to-one linkage between how much water is present and with what energy that water is held. Therefore, it should also related to what is the energy state, or in other words, what is the potential of water which is present in a specific location in a specific point of time. So just like for the saturated case, you can have both steady and unsteady or transient flow. For the unsaturated cases also, you can have this steady and unsaturated flow. So these four dynamic cases, whether it's a steady or in other words, an equilibrium condition or not an equilibrium condition or a transient condition, we should be, in a position to develop the quantitative relationships between how water moves and in other words, at what rate water is moving and what is their time dependent nature if it's an unsteady flow. So, so let us start with the, fundamental principle that we have dealt with describing the energy state of water. We have defined earlier that the soil water potential head or soil water potential or a pressure potential, whichever way you want to describe the energy state of water in soil, in terms of a specific potential energy. So, simplest one is the soil water potential head, because it has a length unit, much similar to the depth of water or depth of rainfall, just that it sort of expresses energy content per unit weight in kind of a length unit. So it's kind of a convenient way to really think about it. And so we have earlier described that water would move from a point in space, say S1 to a different point, and S2, because of this in the influence of this net force which act on that water, and so this force is going to cause that water to move. So you will involve, you will have, it would have a displacement, this delta S. And these two basically vector quantities, of course, should have some kind of a, you could have a specific angle between them, and then you could therefore look at, whenever looking at the energy involved with that net force in terms of a dot product of these two forces, two vector quantities, the force vector and the displacement vector. We have earlier discussed that for each of these component of the forces, you can have a corresponding component of the potential heads, and so you could have a gravitational component for the potential head, and you could have a metric potential head, and osmotic and a pneumatic potential head. So these four components of total potential head we have already recognized. One of the interesting thing that if you you can observe from this general expression for the total potential head is that you could you basically rearrange this equation in terms of a in terms of the this differential or of the total potential head with respect to this spatial coordinate S. In other words, when you are looking at this potential head function, the total potential head function, you are taking basically a gradient of that function, is essentially a measure of the net force which is involved in moving that water from location S1 to S2. So, very clearly what you see here is that if this magnitude of this potential head gradient, and namely the total potential head gradient, is a measure of how much force is involved in moving the water, and this is a really starting point, nice starting point to describe the flow process. So Darcy, a French civil engineer back in the 18th century, observed that the amount of water, so the volume of water which the volume of this volume of water, which can move for unit time t, we call it this big Q, or we also call this as the flux. This flux is directly proportional to this gradient of the total potential head, right? Of course, because gradient of the total potential head is the driving force. Greater is the driving force, more quickly water is going to move, and so therefore more quickly means, of course, it will involve more amount of water. So that's sort of a notion that the rate of flow of water would be directly proportional to the driving force, which is equivalent to the total potential head gradient. And again, you need to recognize that it is the total potential head, not because anytime something is moving, it's the net force that is operational. And so when we talk about net force, we talk about all the components of those forces. So therefore, each component would have a corresponding potential, and so therefore when you look at in terms of potentials, this net force is going to translate to the total potential, right? So therefore it is the gradient of the total potential head, not a single potential, right? So that's the first relationship, that the flow rate or the flux is directly proportional to the gradient of the total potential head. The second thing also one could really imagine that the amount of water which would flow, if the cross-sectional area available for that water to flow is more, of course, more volume of water is going to move. Therefore, there is also a direct relationship direct proportionality between the flux Q and the cross-sectional area A, which is normal to the direction of flow. And it's very important to recognize that this cross-sectional area must be normal to the direction of flow, right? That's, that's the second relationship that you need to come across. There is also, the material, because we know that soil is a porous medium and the pore sizes are small. The whole point of considering potential energy is because the flow, the pore spaces are small, so there is there is sort of a resistance for water to move, so much so that the velocity component in each pore is very small. If you're looking at that is how we have we generally disregard the kinetic energy component of the potential of the total energy, and so only look at potential energy. And so therefore, these small pore structure, smaller size of the pore would resist that water. So therefore, there would be an inverse proportionality between the flux and the the flow rate, or the resistance, flow rate with the resistance to flow. In other words, this inverse of the resistance to flow, which we could coin this term conductivity. So how resistance would be the inverse of the conductivity, and vice versa. The conductivity would describe the ease of water, ease with which water would flow through a specific porous medium. Otherwise, a particular soil, how less or how more conductive, how much it really opposes or helps the flow process. If it helps, that means it's a more conductive. If it is opposes more, it's less conductive, more resistive in nature. So these three things, the flow rate directly proportional to the gradient of the total potential head, directly proportional to the cross-sectional area normal to the direction of flow, and directly proportional to the conductivity of the medium, therefore can be combined to something called the Darcy's law, which tells us that the flow rate, this capital Q per unit area normal to the direction of flow, is equal to a conductivity times the total potential head gradient. Observe that a couple of things here to observe. We have now divided this big Q with the cross-sectional area, so that we are only looking at the intrinsic part of the flow process itself. Only the two intrinsic part here. One is the conductivity, and one is the driving force, right? One, how what really drives water, and who opposes the water to flow, who opposes the flow of water. And so this Q over A, sometime you can think of it's kind of a like a specific flux, or you can think about, and we call it, we call it a flux density. So you can see that it's the volume of water moving per unit area per unit time. Again, this flux density, small q, that we have written here, is has a dimension of length over time. We know that the total potential head gradient, it's a gradient because and head is in the dimension of length, and so the gradient term is dimensionless. So therefore, the conductivity ought to have the dimension of this small q, which is the dimension of the length over time, right? So therefore, you can think about a conductivity which is equal to this flux density per unit gradient, right? So if you think about the gradient somehow is equal to 1, conductivity is numerically equal to the flux density. So how many centimeter of water it is allowing, so a specific soil is allowing to flow through a soil, right? So now we also, as we have mentioned earlier, this potential head here is, there are four components: the gravitational potential head, this contact between soil and water, water and water gives rise to the metric or hydrostatic or pressure potential heads. Then, of course, the solutes are the, this gives rise to the presence of solute in water gives rise to an osmotic potential head, and this, presence of compressed or expanded air gives rise to the notion of the pneumatic potential head, right? And so Darcy's equation, basically describes the flow of water in a saturated soil under steady state conditions. So this equation holds good as long as the flow rate or the flux density remains constant with time, and so therefore, saturated hydraulic conductivity is the property of the media when this soil, all the pores in soil is fully occupied by water, so it's saturated. That's why Ks is called the saturated hydraulic conductivity. Pore space remaining constant for a specific soil at specific time or condition, therefore, would mean that in order to have this constant flow rate, in order to have this steady flow rate, you ought to have this this gradient a constant quantity. That means this potential head, ought to be a linear function of this spatial coordinate, right? Because anytime a gradient equal to constant means that function, gradient of a function constant means that the function is the linear function, right? That's how you get a constant gradient, right? Okay, so this is the Darcy's equation. For many practical scenarios, you will come across that the pneumatic potential is almost equal to zero. Unless the soil is a salt affected soil, the solute concentrations, specifically the solute concentrations in the soil solution phase, are not really high enough to really set in an osmotic potential head. So you could think about osmotic potential is also negligible for soils which are not salt affected. But of course, when you have a salt affected soils, the osmotic component, you cannot ignore it. If you look at out of these four components of the total potential head, the two components, the gravitational potential head, and because we are talking about a saturated condition, so this we are talking about this interaction term between the water and soil has to be a hydrostatic. Has to be a pressure potential head. Okay, and so which is an HP here. Okay, as opposed to a metric potential head. So you can think about a hydrostatic head present on the soil surface, for instance. You also recall that whenever we have to talk about these by the way, this some of these gravitational potential head and the pressure potential head sometimes is referred to as the hydraulic head. This sometimes I'll be using this capital H for some of this gravitational potential head and pressure potential head or hydrostatic head. We have already seen that if we really consider the reference potential head for the gravitational potential to be zero at an arbitrarily set zero point along the z-axis, the gravitational potential head equals to numerically equals to the z itself that we have shown earlier, and so anywhere you have this Hg, you could essentially replace that with a z here. So that is one thing that you should think about. Similar to this reference potential head for Hg, one has to really also look at the reference potential at HP. HP should be zero whenever the water surface is exposed to the atmosphere. So you have a free water surface. At free water surface, the reference potential head for the pressure potential is equal to 0. So if you really plug this Z Hg equal to Z, and up here you see that this Darcy's equation basically equals to the conductivity times this potential gradient because of the the pressure potential, and unity that is because of this gravitational potential gradient, right? So you can think about that for some reason, for any situation, if you could really see that this pressure potential head gradient goes to 0, if you could really have a scenario like that, at those cases the Q, it would be equal, numerically should be equal to the saturated hydraulic conductivity. So that is actually this unit gradient condition. So one of this unit gradient condition essentially is a scenario where this dHPdZ equal to 0, right? There is no potential gradient because of the pressure component of the or the capillary or the metric potential component of the, or in other words, surface tension component of the potential, total potential, right? So so this is how you describe Darcy's equation, as I mentioned earlier. Therefore, having a relationship between the fluxes and the potential gradients, the slope of that line should be equal to the conductivity of that of a medium. Typically, you will see that if the slope is large, that means for a sandy soil, you will see that conductivity is large. So similarly, a clay soil would have smaller conductivity, a smaller slope, as is illustrated in this graph here. Classification, if you look at the saturated hydraulic conductivity, one of the very well studied parameters for almost a century now, beginning with the concepts put forward sometime in 1930s and 40s. We have measured saturated hydraulic conductivity of soils for many locations, and we have classified them from very slow to very rapid in terms of this one of the most frequently used classification system for saturated hydraulic conductivity is given by O'Neill as back as in 1949. So you can see that saturated hydraulic conductivity is one of the very well studied parameters for soil. It's one of the fundamental soil hydraulic properties. Okay. So let's kind of try to understand a bit more about what really constitutes the saturated hydraulic conductivity. Many of you guys perhaps know the equation for describing the flow rate through a pipe. If you have a pressure different across the pipe, Hagen and Poiseuille's law tells us that the flow rate is directly proportional to the fourth power of the radius of the pipe. So in a sense, you have a relationship between you have a relationship between the flow rate. This is the volume of water moving per unit time with this radius of this pipe, and the pressure difference across that cylindrical pipe that you may have. It's pi r4 over 8 eta divided by delta p over L. You could simply replace this L with a L minus 0, so that becomes kind of a difference in the spatial coordinate. So I'm just writing it at delta x here to so that would be what it's essentially the length of the pipe, right? We also know that the pressure difference, um, the the pressure difference, is pressure is essentially a potential energy per unit volume, right? So if you were to really convert that potential energy per unit volume to a which is a pressure potential, into a potential head, all we have to do is we have to multiply. We have to really multiply this delta H with rho g. Rho is the density of water, g is the gravitational constant, acceleration due to gravity, and you can see that I can pretty much rewrite this process law in terms of I could divide that all through by pi r square. So this pi vanishes. I have, in place of r to the power 4, I have an r square. I have a delta p over delta x. And now I'm bringing in this, in place of delta p, I'm bringing in this rho g times delta h. And so I have a quantity which is rho g r square over 8 eta. And so I could really now separate out these properties of water, which is rho here, the density of water, and the viscosity of water. So these are actually property of the water. G is a constant, and this R basically is what? The radius of the pipe, and so the Hagen process law is for a single pipe, right? And we know that in our case of soils, we think soil to be a bundle of capillaries, right? So maybe I could have introduced n number of such pipes here, maybe each pipe having their individual the ith radius, and so this total component could look something like number of pipes times the ri to the power 2, right? So nevertheless, what I'm doing is that I'm retaining this gradient part of it, and then separating these constants into two parts, right? Well, this really gives me a chance to look at this conductivity consisting this flow equation in terms of three quantities. One that really describes the property of the fluid, the other that describes the nature of the pore space, and the last one is the gradient, the driving force that moves the water from one location to the other, right? And well, these three quantities are so now we could really see, draw some similarity between the Darcy's equation. You can think that this driving force up here is also there in the Darcy's equation, right? So if you can really think about this conductivity, as equal to this whole term here up to this here, right? You can think about this conductivity, therefore, is equal to all these fluid terms, and this some kind of a soil property term, the porosity part of it, right? So therefore, we call this fluid part of it as fluidity. The soil pore geometry part of it, we call it an intrinsic permeability. Intrinsic, it is exclusively related to the geometry of the pores, okay? And fluidity is exclusively related to the fluid property, the property of the fluid. So in our case, it's water, right? And permeability is, of course, the soil pore structure, right? And so therefore, one could think about conductivity to be a product of fluidity and intrinsic permeability, right? Rho g over eta, which is the viscosity, coefficient of viscosity, and that is related to the radius of the pore spaces, right? And how the pores radius is distributed, for instance, in soil. So you can easily see that, of course, when you're talking about this, of course, when we are kind of drawing this equivalence between the Hagen-Poiseuille's law with the Darcy's equation, we are actually talking about those pore spaces through which water moves, right? So this radius, though, you need to think about, it's not just any pore. It is the pore which is conducting water. Of course, if the pore is conducting water, that pore really contains water, right? So we are kind of talking about the pores of the radius of the water containing pores, right? That's important because not all pore spaces may contain water. Of course, when the soil is fully saturated, all the pores contain water, right? So if you can think about a radius of a pore which is of a maximum size, so maybe an R max, you're talking about all pores smaller than and inclusive of this R max contain water containing pores. That's when soil is fully saturated. And so when you talk about a saturated hydraulic conductivity, you talk about this R to be the maximum possible size of the pore which is present in the soil, which is also saturated, right? But what happens, if for a so what you have? So you have this pore sizes, from 0 to some kind of an R max, R max, right? Writing it with my mouse. All right. But you could have all these pore sizes contain water, but you could also have scenarios where only pore sizes which are smaller than this R, which is up to here. All these may be containing water, right? And from here to here, these are empty, for example. So in soil is at field capacity, all large pores are empty, so you can easily now see that this conductivity ought to decrease because this R is now reduced from R max, but this decrease in the conductivity would really decrease as a sort of a square function, right? Because it is a function of R square. Okay, it's a function of R square. So if you are looking at the conductivity of a saturated soil versus a conductivity of an unsaturated soil, of course the unsaturated soil, the conductivity would drastically decrease from the saturated. It would decrease with a square function of R, right? And so therefore therefore the relationship between the conductivity and this pore size would be a non-linear one. Now what, the way we describe this pore size here in the context of water flow, we sort of characterize it with the water containing pore, right? So if not all the pore spaces contain water, that's what we are talking about. So the amount of water present in soil is going to be less than the saturated water content, right? And so therefore the conductivity would drastically reduce with the radius of the water containing pore, drastically also reduce with the reduction in the soil wetness. But we also know that from water retention characteristic, the wetness of a soil is uniquely related to the energy content of the soil. So in other words, in an unsaturated soil, you will also see this non-linear relationship between the potential head and the conductivity, right? So you are going to, so all of these, whether it's the pore size, whether it's the amount of water, whether it is the potential of soil water, all are going to be linked to this conductivity function through this sort of a non-linear relationship between the conductivity and permeabilities, right? So it's the intrinsic permeability that will change, right? Because fluidity for water would almost remain the constant, except some of the temperature dependencies because of the viscosity depending on temperature, density of water depending on temperature, right? Otherwise, at an isothermal condition, you will see that the fluidity of water would remain constant. It's the intrinsic permeability that would change, that would really give rise to different values of conductivities, and the degree of saturation it is going to give you the conductivity. So all that Darcy's equation is, of course, for the saturated condition. But what happens? Soil is not always remaining saturated. Now, Darcy's equation can be also modified to describe water flow in the unsaturated soil. In 1911, Buckingham came in and he showed that, well, the same Darcy's equation, the same form of the Darcy's equation, you could almost use, to describe the flow rate in the unsaturated soil under steady condition. Of course, you still have this conductivity part, right? You have a conductivity term, you have a gradient term. This nabla H is this upside down delta or triangle is called a nabla, Greek letter. So this tells us the gradient of H, right? So this is hydraulic. I'm writing it as a hydraulic head here. So you can have this as long as though this Q is now a function of H, because now the soil wetness changes because soil is no longer saturated, right? Soil is no longer saturated. So soil is no longer saturated, and as you know, the conductivity is less than the saturated conductivity. So and of course, the potential heads are no longer the pressure potential, rather it is the unsaturated scenario. It's the metric potential is not now dominating. So therefore, you have the same Darcy's equation. Now it's a Darcy-Buckingham equation, and it has got a few changes. The first one being the saturated hydraulic conductivity is replaced with an unsaturated hydraulic conductivity. The pressure potential head, so gravitational potential head is not affected. Only the pressure potential head is now changed to the metric potential head. It's now from positive to negative, and of course, once you do that, this whole thing also works. Okay, that is but of course, it has to be steady state. Well, so under this steady state now, therefore, our conductivity has to, this hydraulic conductivity has to be a function of the potential head, So as I was mentioning earlier, because this water containing pore size is going to reduce, corresponding the H values is going to be becoming negatively larger, right? Water content is going to go down. So similar to a water retention characteristic, you will get a characteristic curve for the hydraulic conductivity as a function of the pressure head, or a function of the pore size, or a function of the soil wetness. Of course, when soil is saturated, that means H equal to 0, the hydraulic conductivity would register the maximum value, that would be K sat. So this relative hydraulic conductivity, which is basically K over K sat, should assume a value of 1, and you can have a relationship between this degree of saturation SE and conductivity. Remember, SE is equal to theta minus theta R divided by theta S minus theta R. So the effect ratio of the effective soil wetness and effective soil wetness at saturation. So this is again, the second soil hydraulic properties that you come across in addition to the water retention behavior, right? Water retention characteristics and soil hydraulic properties of unsaturated soils are two, primary hydraulic properties of soil that you need to really understand and have to have quantification must be done so that you will be able to, describe the, water flow, whether in terms of Darcy's equation or in terms of, Darcy-Buckingham equation, right? Okay, well, in these steady state, relationships, whether it's a Darcy's equation, whether it's a Darcy-Buckingham equation, they are they are also similar to other steady state form of the transport equations. For example, when you are looking at diffusion of solute, the Fick's law of diffusion tells you that the amount of solute which diffuses per unit time per unit cross-sectional area normal to the direction of flow is proportional to the concentration gradient, which is the driving force, and directly proportional to the diffusivity or molecular diffusion coefficient of that solute. Similarly, when you are looking at the conduction of heat, for example, the Fourier's law, it states that the amount of heat energy which moves per unit or which gets conducted because of the thermal molecular motion, per unit time per unit cross-sectional area, again normal to the direction of flow, is a product of the thermal conductivity and temperature gradient. So these are the steady state form of the expressions that you can really use for describing different processes, right? But these are all with regard to the steady state. But as we know, hardly the flow rate remains constant in soil, hardly the water content remains constant in soil, hardly the potential heads remain constant in soil, and so you always look at a sort of a dynamic condition, a transient condition. You always have an unsteady condition, unsteady, unsaturated condition. Well, that sort of a thing can also be described. A quantitative and mechanistic description can be also built up, using these simple mass balance or conservation of mass sort of relationships. You know that if you look at a unit soil volume, the change of soil wetness which would take place in a soil in that volume would be because maybe some water comes in and some water comes out. We talked about field water balance, right? It's in a macroscopic sense. So you could really make a microscopic sense in make this unit soil volume to be very, very small, and sort of do a invoke a conservation of mass, and mass balance. You would How would you write that? You would write that the storage change, or the change in the soil wetness that takes place in this control volume, should be because some water is coming in and some water is going out, right? And so this balance between these two, you could pretty much write. Well, how do you write that? How much water is coming in? Well, you could really find out how much ever water which is present in that soil over a over this time duration, the water went came in and went out. So basically, how do we really write our volumetric water content? The volume of water divided by the total volume of soil. So the total volume of this volume element is delta x, delta y, delta z. So this left hand side tells us how much water really changed over this delta t time, in terms of what volume of water. Similarly, you look at the right hand side of it. This tells you, because a flux density is what? Volume of water entering per unit time, per unit cross sectional area, per unit volume of water per unit time per unit cross sectional area. So therefore, I could really multiply this unit cross sectional area normal to the direction of flow. So this is the unit cross sectional area normal to the direction of flow, delta y times delta x, and you multiply delta t. So this right hand side also becomes a volume of water, right? And so therefore one could really cancels out this delta x and delta y, bring this delta t this side, and of course you could do this delta z that side, and then of course you do this limiting case, set delta z to equal to 0, and bring in place of this q the Darcy-Buckingham equation. That is the expression q, and develop a complete mechanistic description of water under transient condition, which is called the Richards equation, for unsaturated soil under transient water flow condition. And solution to this kind of a problem, is kind of more involved and beyond the scope of this class. So I will not really get into the Richards equation much. Maybe try to give you some notion about how these kind of relationships would describe our hydrologic processes. Now, when you look at this field water balance equation that we talked about, field water balance equations we talked about, we know that the storage change in a change that takes place in a soil is a result of what? All these hydrologic processes, whether how water is added through, whether it's an irrigation water, whether it's a rainfall, water infiltrating across the soil surface, and water getting lost because of the deep percolation or drainage. So each one of those because of the evapotranspiration, each one of those is a hydrologic event, right? And so you also saw in derivations of the Richards equation, we were kind of looking at how the soil changes its soil wetness related to the fluxes of water coming in and going out. So it's to give you kind of an example of water infiltration. We know that infiltration means how water actually moves from the air phase into the soil phase. So it's a boundary phenomena. It's a soil surface. It's a soil surface phenomena. Whatever is happening, how the water goes from the gaseous stage, the air, to a solid phase, right? It's from gaseous phase to solid phase. So it's a kind of a water is moving from one phase to the other. Is the process of infiltration. So of course, if you have excess water, it would run up. So how would you really describe this infiltration process? So let us kind of see how you can do it with a simple example. Here we sort of kind of give you a very simplified condition. So let's say if you have a soil, if you have some kind of a standing water, of course water is going to start infiltrating through the soil surface inside, and imagine that this water is freely coming out at the bottom of the soil. So how do we really use the Darcy's law for this? We should follow 3 simple steps. First, we should identify 2 locations in the soil column across which we wish to really apply this Darcy's law. Second thing, we should really identify what are the components which is driving the water. So basically, all the components of total potential head, all their reference potentials, we should really identify. Then, of course, we need to really think about what is the coordinate system, so that we know directions for the flow rates, so that we know whether it's a deep percolation or whether it's an evaporation, for example. So identifying how the components of the total potential in this particular case. So we are going to apply this Darcy's equation with across A and B. So we need to therefore know what are the potentials at A and what are the potential at B. We know that here water is moving downward, so there is a gravitational potential involved. We also know that there is a standing water, so therefore a pressure potential is involved. Of course, the reference, we can set it arbitrarily for gravity. Free water surface is the reference potential for the pressure potential, and so we could, from here, we could really write down all the components of potential at A and B. So here Hg equal to 0, Hg at B should be equal to Z, so that should be your AB. Hp should be this BC up here. Hp at A should be 0, and you sum these two. Now you have the Ht at A and B, and you know this Z equal to 0 at A, Z equal to AB at B. So now you can really put all these into a Darcy's equation. So very, very, very simple. Well, things can be a bit complicated when you really use the Darcy, go to the Darcy-Buckingham type of equation, because remember in the Darcy-Buckingham type equation you have to really have a conductivity which would depend on the nature of say for example nature of the degree of saturation, for example. So if you really bring in a water retention characteristic, maybe an exponential function of H and an exponential function of conductivity as an H, you should be able to calculate, given what is theta s, what is theta r, what are these constants for the retention curve, what is the hydraulic conductivity at saturation. Here is another constant for the unsaturated hydraulic conductivity function. So for every pressure potential head, you can really build this water retention characteristics and hydraulic conductivity functions, and then of course if you are considering a horizontal infiltration, you should only horizontal component, so that there is no +1 involved, and you could do all these math and should be in a position to describe the potential head as a function of the properties of the hydraulic properties of the soil. Similarly, if you really want to bring in a vertical infiltration case, so that you don't neglect the gravity, and these expressions become a little bit more complicated, right? As you can see that the steady state scenarios are become quite involved, but nevertheless, if you just go through some of these maths, it would be pretty straightforward for you to look at how water moves through the soil. But for the Richards equation, if you have to really work with, things become kind of more complicated. You can see that, if you're looking at it, so you need those simulation environments. So here is a simulation scenario for the infiltration. So you can think about, like a soil, a two-dimensional soil up here. So you are adding, say, water up in this area, and if you allow that water to move to an initially dry soil, you will see that slowly what would happen is that waterfront is going to move downward as well as to the sidewise laterally, and this beautiful pattern of soil water movement you can see if you really look when you go to maybe using some kind of a simulation environment. All right, so I don't want to really spend more time on how to really deal with the Richards equation. Is a topic that you need to really study more details in higher classes. So kind of summarizing, these all these concepts of water flow gives you sort of impression about how water movement can be described in terms of potential gradients, conductivities, retention characteristics. We saw the nature of Darcy's equation, and of course didn't go to the Richards equation much, but you need to if you want to really use a specific form of these mechanistic relationships for describing a specific hydrologic event, you need to really put all them together in very systematic manner, and that allows you to really estimate the soil wetness or soil water potential as a function of time and space. Obviously you need more simulation environment, and you need also more exposure on how to deal with water flow in soil. So it's very, very interesting area to really expand our knowledge. I hope that some of you really get very interested in the water, because water is a very, very fundamental thing in our life. And I hope you spend some time looking at what happens to water in soil and how they really move in our environment, because they really influence a lot of different events in our natural resources. So try to really give you an overview of soil wetness, soil water regime, and water flow processes in these few lectures. And I hope that you get more interested to learn more about soil water flow and soil water regime in soil. Okay, that's all I have. I hope you enjoyed it. I will see you in the next class.